In this video, I'll be working through Module 8 in the course pack. First, I'd like to remind you of a couple things that you saw in the looking forward in Module 7. On page 99, we introduced another mathematical model, an exponential model. It has a slightly different equation than the linear model we worked with in Module 7. On page 100, we defined what the variables in that model represent. And then through the subsequent examples, you got a little bit of practice doing some calculations with the exponential model. In problem 9 on page 101, you use this mathematical tool called a logarithm as necessary. And so I'm hoping that since you've completed the looking forward, you're feeling pretty comfortable with dealing with exponential models. And so in Module 8, we're going to continue discussing exponential models, work through a couple more examples, and see a few examples where we modify the model from its standard structure. Let's get started. The first example, example 8.1, we're returning to the context of advertising and how that influences retail sales. I like to begin every problem by stating the list of variables that I'll be using. Since I'm dealing with an exponential model, I'll have a y sub 0 or y naught, an r, and an x. I also like to take a second, this isn't necessary, but I like to take a second to define what the variables represent. Here, my y dependent variable represents sales values, while my x independent variable represents time. Grabbing some details from the problem, I notice I've got a rate of 3%. Remember that you always have to represent that rate as a decimal, so I'll write that as 0.03. It says that the current or initial sales values are 2,800. So I'm going to use that as my y sub 0. My y sub 0 is always my starting value. And then we want to know how much he could expect after 6 weeks of advertising. So the time interval here will be 6 weeks. The variable we want to solve for is the final value of sales. So I'll indicate that in my list by just putting 3 question marks here for y. Now I can plug all of those details into the equation for the exponential model. And I could do some simplification. And I see that the final sales value after 6 weeks will be approximately $3,343.35. For the next example, I've actually done the work already, so I'll just talk through my solution. In example 8.2, my dependent variable is the volume of a handbell. My independent variable is time. We have a rate of 12.6%, but that's the rate at which our quantity volume decreases. So in my formula, I've written that rate as a negative value. I have a starting value of 84 decibels, and I want to know what the value will be 6 seconds later. Plugging in and simplifying, I get a volume of approximately 37.441 decibels. To the right, I've included a small graph. This isn't necessary, but I just use it as reference to put these values that I've calculated into context. I started with a volume of 84 decibels. The volume is decreasing exponentially, and after 6 seconds, I have a resulting volume of 37.4 decibels. Let's take a look at the next example. I have some of the details for example 8.3 already written out here. I'm analyzing the size of a bacteria population. We're given that the growth rate is 4.8% and my independent variable is time. The tricky detail about this problem is that it does not state a specific starting value or a specific final value. Instead, it simply indicates that we want the population to triple. I have a little flexibility in how I set this problem up. I can actually select any set of values for the initial and final populations so long as they stand in this relationship. For example, if I wanted to, I could choose my starting population to be something simple, say 10, and then the final population would have to be 3 times that. So I'd have to have a final population of 30 in order to capture the relationship that the population is going to triple. If I wanted to choose other values for y sub 0 and y, I could, so long as they stood in this same relationship. Now I can plug these values into my equation and do some simplification. At this point, the variable I'm interested in solving for is in the exponent, When I find myself in that situation, I know that I have to take the logarithm of both sides. And now, an important property of logarithms allows me to take this exponent, which is inside the logarithm, and move it to the front as a coefficient. So my final step will be to divide both sides by this number in order to isolate x. Now I can plug that in my calculator to get an approximate value. So I get an approximate final value of 23.441. Looking back at the statement of the problem, I notice that the units on my x value are days. So this will be approximately 23 days in order for any initial population to triple in size. Let's take a look at the next example. In example 8.4, there's two calculations that we need to complete. There's a calculation for the 1990s and then a calculation since the year 2000. So I have set up two separate sets of variables. Let's read what the problem says. It says during the 1990s, Flagstaff's population grew at a steady rate of approximately 2.4%. Strangely, the population then dropped by roughly 4,000 residents during the year 1999. Since the year 2000, the growth rate has been a modest 1.5%. If there were approximately 46,000 residents in Flagstaff in 1990, how many are there now? Notice that this 46,000 is the number of residents in 1990, so I'll use that as my initial population value for the 1990s. And then thinking about the structure of the problem, if I can calculate the final value for the population in the 1990s, that will determine what the starting value is for the 2000s. I have an additional detail which indicates that during the year 1999, the population dropped by 4,000 residents. So I think my initial calculations here will be for the 9 years from the beginning of 1990 through the beginning of 1999. Plugging these values into my equation for an exponential I have. So these calculations indicate that at the beginning of the year 1999, I would have a population of 56,945. I've written the decimal here, but in the context it doesn't really make sense to include a decimal, so I will utilize just the whole number part of this value. So notice then that during the year 1999, the population dropped by 4,000. So in order to determine what my starting population will be for the 2000s, I'm going to take the 56,945 and then I'm going to subtract off 4,000. This yields a population of 52,945, and that will become my initial population for the 2000s. Let's project forward to the beginning of the year 2020. So my x value will be 20 in order to calculate from the beginning of the 2000s to the beginning of this year. And then the final value for the population is what I'm trying to calculate. Let's plug this information into the formula and simplify. So my final value is 71,309.238. Again, in this context, it doesn't really make sense to utilize a decimal, so I'll round to get 71,309 residents of Flagstaff. Let's take a look at the next example. In example 8.5, I once again have two separate calculations, two related calculations. I have an inflation calculation for the 1950s and a similar calculation for the 1980s. In the 1950s, I'm told that a standard set of goods rose in price from $24.10 to $29.60. I'll input those as my starting and final values for the cost over the course of that decade. I'm now considering the 50s to be the entire 10-year period, so I'll use a time value of 10, and the rate at which prices increased is what I'm trying to solve for. So I can take these values and plug them into my equation and simplify. The next step that I need to complete algebraically is a little tricky. Right now I have this quantity raised to the 10th power. In order to eliminate that 10th power, I'm going to be essentially taking the 10th root. And the way that I write that is that I raise both sides to the 1/10th power. This yields the following expression. Notice that on the right-hand side, the 10th power and the 1/10th power will multiply together to give me a 1th power or first power, and so I won't bother writing that. On the right-hand side, I'll simply have 1 plus r. Therefore, in order to isolate r, I can just subtract 1 from both sides, yielding a final value of 0.0208. This is my inflation rate for the 1950s. So I would say the 1950s had inflation of approximately 2%. The problem provides similar information for the 1980s. I want to utilize the similarity between these two problems to note that the algebraic steps that I would need to do for the 1980s would be essentially the same as I just conducted over here for the 1950s. So I'm going to try to jump down and maybe borrow the structure of this final calculation and see if I can write out the corresponding value for the 1980s. Now I could put this into my calculator to get an approximate value, yielding a final value of 0.0472. So I would say that the inflation rate for the 1980s was about 4.7%. So the 1980s had a much higher inflation rate.